You might have heard the expression, calculate to 6 decimal places, measure with a micrometer, mark with chalk, and cut with an axe. Although it is obviously an exaggeration, this statement expresses the very valid point that precision decreases as we progress from analysis or design to measurement and implementation. In the next few minutes, we will address 2 related questions. In RF engineering, how many decimal places should we use when we are working in decibels? And what happens when we convert rounded values from decibels back to ratios or absolute units, such as watts or volts? You will gain the knowledge needed to decide for yourself how many decimal places to use, depending on the requirements of your specific task. Please see the video description for a full list of disclaimers, including the ones here, plus a timeline and helpful resources and links. Please support the channel by using our affiliate links. Using the 3 equations shown here, we have prepared an Excel spreadsheet to help answer the question. Both power ratios and voltage ratios are considered. The spreadsheet has 10 columns. The first column, column A, specifies the number of decimal places to be used in the rounded dB value. Here, -1 indicates that we will round to the nearest 10 dB. 0 indicates that we will round to the nearest dB, and the larger numbers indicate the number of digits after the decimal point in the rounded dB values. The second column is an example dB value to be rounded. We can set this to any value. The next column, column C, is the power ratio that corresponds to the example dB value before rounding. The fourth column contains the voltage ratio that corresponds to the example dB value before rounding. In the fifth column, we have the example dB value rounded to the number of decimal places shown in column 1. In column 5, you can see that all of the digits after the specified number of decimal places are set to 0. The sixth column, column F, contains the power ratio that corresponds to the rounded dB value. The seventh column, column G, shows the voltage ratio that corresponds to the rounded dB value. In this column, as well as in column 4, we assume that the voltages are measured for equal reference impedances. The eighth column indicates the error in dB introduced by rounding. The ninth column shows the percent error in the power ratio that is introduced by rounding the example dB value. Finally, in the 10th column, we have the percent error in the voltage ratio due to rounding the example dB value. We would expect the maximum roundoff error to occur when the dB value to be rounded is halfway between 2 dB values that have the specified number of decimal places. We can observe this in the spreadsheet. Also, it turns out that the maximum error occurs when we round up from the midpoint between these values. And this is true regardless of the number of decimal places to be used in the rounded value. For example, when rounding to the nearest 0.1 dB, the error introduced by rounding up from 0.5 dB to 0.1 dB is greater than the error introduced by rounding down from 0.0499999 to 0.0 dB. You can try this yourself by subscribing and using the spreadsheet, or by calculating the errors yourself using the provided equations. Also, adding any positive or negative integer number of decibels to the dB value to be rounded does not change the error introduced by rounding to the specified number of decimal places. And for negative dB values, rounding up, for example, from negative 0.499999 rather than rounding down from negative 0.5 results in a larger error that is the same as the error for rounding up positive dB values that end in 0.5. Rounding to the nearest 10 dB is equivalent to rounding to the nearest bell. The bell is a unit on which the decibel is based, where 10 dB equals 1 bell. We see that rounding to the nearest bell can introduce an error in the power ratio of over 200% and an error in the voltage ratio of over 75%. Although rounding to the nearest bell does preserve the rough order of magnitude of the initial ratios, this is a very rough approximation, and it would not be accurate enough for use in measurement, analysis, or design. By rounding to the nearest decibel, we reduce the maximum power error to about 12.2% and the maximum voltage error to about 5.9%. This gives a closer approximation that might be sufficient for preliminary calculation. From this point, each additional decimal place that we use in the rounded value reduces both the power and voltage ratio errors by about a factor of 10. Rounding to the nearest tenth of a dB results in a maximum power error of about 1.2% and a maximum voltage error of 0.58%. Rounding to the nearest hundredth of a dB gives a maximum power error of about 0.12% and a maximum voltage error of 0.058%, and so on. For most applications, 1 or 2 decimal places should be sufficient. Few, if any, applications would use more than 2 decimal places, in part because gains and losses of RF components used in wireless systems are rarely specified with such high precision. To understand this better, we can take a quick look at specifications from the datasheet for a Keysight step attenuator. Typical repeatability of this step attenuator is specified to be 0.03 dB over a maximum lifespan of 5 million cycles per section. Also, the minimum attenuation step size available in this product is 1 dB. We also see that insertion loss when the attenuator is set to 0 dB is 0.8 dB plus 0.04 dB per gigahertz, and that Keysight considers this to be exceptionally low. Therefore, if decibel values obtained from measurements using this step attenuator were rounded to 3 or more decimal places, the numbers in the third decimal place and any following decimal places would not be meaningful. For this mini-circuit's low-noise amplifier, specifications are rounded to the nearest 0.5 dB. Also, values are specified for minimum and typical gain, and these values represent a range of as much as 5.5 dB, depending on the frequency range considered. Keysight and mini-circuits produce high-quality products that are used in many systems and measurements. So, from the specifications, we can see that it would be very difficult to build and measure or calibrate a system whose parameters are specified to within less than 0.1 dB using these amplifiers and step attenuators. To summarize, practical implementations and measurements typically involve dB values that are less precise than those we could calculate in an analysis or use in a design. Using 0, 1, or 2 decimal places in our dB values results in maximum power errors of approximately 12%, 1.2%, and 0.12% respectively. The corresponding maximum voltage errors are about 5.9%, 0.58%, and 0.058%. Each additional decimal place decreases the maximum error by about a factor of 10. However, due to limited precision and variability of hardware used in measurements and system implementation, using 1 or 2 decimal places to express dB values will be sufficient for most practical applications, such as field measurements or wireless communication system design and development. However, there may be applications related to development of high-precision test equipment and some scientific measurements that would require greater precision. Thank you for your time. We hope that this video has helped answer questions that you might not have seen addressed elsewhere. Please hit like and subscribe and support the channel by using our affiliate link if you plan to buy a featured item. We also provide consulting services and referrals.